Hi, Barry. Good to see you.
Good to see you too.
Wait, am I the host now? I just asked whether I want to admit.
I think you're a co-host now, but I
Okay.
think you can ignore those messages and go ahead and get started when you are ready.
Okay. Thanks, Barry. It's good to see everyone. I can't wait to see all of you in person soon too. So I'm going to talk about, I guess it's more of a quantum Hall inspired problem about the way that skirmions, the sort of skirmions that we're familiar with in the integer quantum Hall effect, quantum Hall ferromagnetism, actually give an interesting topological route to superconductivity, because I want to argue that skirmions can cause electrons to bind into charge 2e pairs in this certain context. But then primarily this is going to be showing the DMRG evidence that this mechanism for superconductivity actually works out in practice. And so I want to acknowledge my collaborators first. Shubhayu Chatterjee is a postdoc at UC Berkeley. He was Subir Sachdev's student before that. He has a deep background in field theory, and he was able to do all the quantum calculations on the skirmions. And Matteo Ippoliti was previously at Stanford. He's now at Vedic Ecumeni was previously at Princeton, is now with Vedic Ecumeni at Stanford, and he's probably the world expert in doing these sort of quantum Hall DMRG numerics we're about to show you. Okay, so the outline for the talk. First thing, I'm going to spend some time presenting the model. It's basically two copies of the quantum Hall effect, but related by time reversal. So the inspiration from this actually came from the physics of magic angle twisted bilayer graphene. So I don't know, the model's a little bit unfamiliar, perhaps, so I'll spend some time unpacking it and how we study it numerically. Then I'll provide the DMRG evidence for there being skirmion-mediated superconductivity in this model. And then finally, if I have time, I'll walk back and translate to how this physics might actually be realized in twisted bilayer graphene. Okay, so what's the model? We're going to start with a familiar starting point. We're going to have two-dimensional electron gas. And I want to start with a four-component electron gas coming from the combination of there being a bilayer as well as spin. So you have a spinful bilayer. Though you should keep in mind that I'm going to call it layer. In an actual physical system, layer might not be realized, literally as layer. It might be, say, an internal orbital degree of freedom. And what I call spin could be some sort of pseudospin, like in the magic angle graphene application, the spin is actually the valley degree of freedom. The next component is the long-range Coulomb interaction. And here the long-range Coulomb interaction is only the total density. So you could think of it as SU4 symmetric. So we're not letting the two layers interact less weakly with each other. And then the final ingredient in the Hamiltonian is I want to put on a weak anti-ferromagnetic coupling between the spin density and the two layers. So the strength of this term is J. And because I'm going to want to be talking about various ordered states, there's going to be anti-ferromagnetism in this model. It's useful to define two fields, n plus and n minus, which just gives the spin density in the top layer and the spin density in the bottom layer. So in that language, we can unpack what this interlayer anti-ferromagnetism is. It's just the difference in the spin densities in the two layer squares, which you've expanded is nothing more than Heisenberg coupling between the two layers, anti-ferromagnetic Heisenberg. Of course, the first two terms, kinetic energy and Coulomb interaction, we do all the time. The anti-ferromagnetism might seem a little bit unnatural, but actually the way you should think of it is, suppose you had a weak amount of tunnel coupling between the two layers. Then just like super exchange generates anti-ferromagnetism in the Hubbard model, perturbatively, that coupling will actually generate exactly this anti-ferromagnetism between these two layers. This was discussed in the physics of spinful quantum Hall bilayers by Sachdev and Desarma back in 1997, actually, the generation of this anti-ferromagnetism. Okay, so that's the model. So far, of course, I'm going to need to turn a magnetic field on. And the twist compared to usual quantum Hall physics is what I want to do is turn on a magnetic field with the opposite sign in the top layer and the bottom layer. Okay, so I wouldn't know how to realize this at 15 Tesla in an actual material. the other way to code this is really I want the bands in the top layer to be churn 1 bands and the bands in the bottom layer to be churn -1 bands. Okay, and the claim is just with that simple switch of the sign of the magnetic field. If you fill the lambda levels of this system up to a density of 2 plus a small amount, which you can think of as doping an insulator, this model is actually going to be a superconductor, even though you have long-range Coulomb interaction, just the 1/r, for any positive value of J, even infinitesimally small. Okay. So I think this is a very interesting result from this simple model, and I want to provide now the numerical evidence for it and how we can understand it based on physics we know and love from the quantum Hall effect, which is the existence of spin skirmions. Okay, so since I'm going to do the numerical proof of this first, that this model is a superconductor, I'll briefly review the model, the algorithm we use. So it's going to be infinite DMRG adapted for lambda levels. So what is the lambda level spectrum of this problem? Okay, so it's 2 spinful bilayers. Now, of course, the lambda level spectrum doesn't actually care about the sign of the magnetic field, B or minus B. So if you just look at the energy of the wave functions, you're going to have 2 copies of the quantum Hall effect, one in layer plus, one in layer minus, that are going to be degenerate. And both of them are going to be spinful. So each of the lambda levels is 4-fold degenerate. So as we fill from 0 to 4, that's when we filled the 0th lambda level. As usual, when we go to large magnetic field, we'll imagine that the Coulomb interaction is weaker than the cyclotron gap, and we're going to project into the lowest lambda level. So the problem is now very similar to standard fractional quantum Hall numerics, except we have 4 components from the spin and bilayer. The only difference is that when you go to compute the Coulomb matrix elements, when you need to complex conjugate the wave functions coming from the bottom layer where the magnetic field is obvious, that changes Coulomb matrix elements, and it turns out that that little change is going to be sufficient to actually make this model a superconductor. Okay, to study it numerically then, we use IDMRG on the cylinder geometry. So we map the 2D problem onto a cylinder of some circumference L. And then in Landau gauge, we know the single particle states. Their center of mass is nicely aligned in a 1D like chain fashion along the cylinder. The only difference coming from the magnetic field being opposite in one of the sectors is that when you write out the Landau gauge wave functions, the relation between the center of mass and the momentum around the cylinder gets flipped in the other sector. So if we label the states by momentum, the states in one layer are moving to the right as you increase the momentum, and the states in the other layer are moving to the left. Nevertheless, it still maps to sort of a 1D fermion chain, and we have these 4 components that you just put together next to each other in a random order, and that's the input to the DMRG model. So we're then going to run infinite DMRG on it. DMRG for the fractional quantum Hall effect is, of course, much older than this. It goes back to at least Shibata back in 2001. So the model we can then handle using our fractional quantum Hall DMRG code, and I just want to thank Roger Mong and Frank Goldman for developing that with me. Okay, so what's the phase diagram? To present the phase diagram, I'm going to actually add one more term to Hamiltonian, just make it slightly more complicated, which is that when I look at the antiferromagnetism, previously I had that the strength of the antiferromagnetism was the same for all 3 spin directions, X, Y, and Z. I'm going to now allow it to actually be easy plane. So I'm going to have a slightly different strength for the X, Y components and the Z components. That degree of XXZ easy plane anisotropy is going to be described by this additional term delta. And then if I express J in terms of the Coulomb energy, EC, the only 2 scales I have in the problem are then J and lambda. So that's going to be the plane in which I draw my phase diagrams. I should just mention that the reason I do this is if we go back to magic angle graphene, the spin degree of freedom is really valley. And valley has a U1 symmetry, which is going to correspond to rotations about the axis, but not full SO3 symmetry. So it was important to consider the more general case here. So here's a schematic of what the phase diagram is going to look like. If you fill 2 plus delta of the Landau levels, rather than forming something like a fractional quantum Hall state, the phase diagram looks like this. If J is big enough above the critical value, the extra electrons actually form a superconductor despite the Coulomb repulsion. Below this J, there's a first order phase transition into a Wigner crystal, which is going to be similar to the Wigner crystals we know from the fractional quantum Hall effect. And in fact, actually, if I go to larger delta, like delta equals 1/2, you can actually get fractional quantum Hall states. But I'm usually going to focus on the smaller delta just to keep things compact. And so that leads to this first order phase boundary between them with a critical value of J, described by this curve in the lambda as a function of lambda. Okay, so let's actually see this sort of data. What we're going to do is for each, we're going to fix some particular degree of doping. This is for 2 + 1/4 filling. And then we're going to measure several order parameters. We're going to test for superconductivity. We're going to test for XY antiferromagnetism between the two layers. And then by looking at the density, we're also going to check for a charge density wave or Wigner crystal. And I'll dive into what these order parameters are in just a second, but a schematic plot of the actual phase diagram you can see here. And indeed, you get strong superconductivity for larger J and the XY ordered charge density wave for smaller values. Okay, so first I want to convince you that if I just pick a point in the phase diagram here above the critical J, that it is in fact a superconductor. So what is the nature of the superconductivity? First, the pairing channel is kind of like S-wave. So when you write down the form of the Cooper pairs, it's pairing electrons, which are directly on top of each other. And the two electrons in the pair, there's going to be one in each layer. And it's then, I don't know if I want to call it spin singlet because the two electrons in the other layer, but it pairs up and down spin in the way we're familiar. Okay, so this is the order parameter. One subtlety when we want to detect it in numerics, though, is because the symmetry that you're breaking is a continuous symmetry, and because I've taken 2D space and I've put it on a cylinder, it's formerly a 1D model, and we know that actually, because of the Merman-Wagner theorem, this order should actually be algebraic. So what we actually test for is we measure the superconducting 4-point function at 2 distant points along the cylinder, and we check to see if there's algebraic order in the superconducting order parameter. That order is going to be described by some exponent eta, which we can then extract by looking at the fall off of the correlations. So here's an example of such superconducting correlations. The x-axis is the distance along the cylinder, measured in units of the magnetic length. And the other slight subtlety here is that when we do DMRG, there's really an accuracy determined by this parameter called the bond dimension. Larger bond dimension is more accurate, but takes longer to run. So what we really need to do is we need to run the numerical simulations for more and more accurate DMRG. And you can see what happens is as the accuracy increases, the superconducting correlations start collapsing onto a very nice power law out to 40 or 50 magnetic lengths or so. Okay, so there's clear evidence for power law superconductivity here, but we can do even better than that. I was showing the results for a particular circumference, but how do we know that this superconductivity is an artifact of a thin cylinder? How do we show that it survives in the thermodynamic limit? So one way to do this is actually to quantitatively look at the scaling of that algebraic exponent. So if you did have a true 2D superconductor described by some finite phase stiffness, you can easily just put that model on a cylinder and predict what is the resulting stiffness of the 1D problem. And from that, using usual results from bosonization, you can work out what the exponent should be. And the takeaway is that if it's a true 2D superconductor, the exponent in 1D should scale as 1/L. So you can see this in this plot to the left. We show the superconducting correlation function at 2 different circumferences. And to the eye, at least, you can see that on this log-log plot, at larger circumference, it falls off more slowly, corresponding to the fact that the exponent has decreased from around 1.4 to 1.0. So we can formalize this into a nice scaling argument to automate the procedure rather than fitting lines by eye. There's a 2-parameter scaling collapse that we can do in the distance and circumference. And you very nicely see that for all circumferences from 8 to 12, which is the largest we can do, we get clear evidence that the exponent scales exactly as 1 over L. So this indicates that the superconductor actually survives in 2D. This itself I actually find rather impressive. I'm not aware of another model with long-range Coulomb repulsion where it's actually been shown that there is electron-mediated superconductivity. Of course, in the context of the hovered model, there's been long history by White and others of studying, using DMRG to study the Hubbard model on circumferences of, say, cylinder 4 and 6. But my understanding at the moment is, say, on circumference 4, they might see they see algebraic superconductivity, but then when they go to a larger circumference 6, they don't see the algebraic superconductivity anymore. So it's quite nice that at least this shows in principle that there can be in the 2D limit purely electron mediated superconductivity. Okay, so what's the evidence for the charge density wave? This is, of course, more straightforward to look at. You can either just directly image the density, or if you want to be more sophisticated, we can look at the density-density correlation function, the pair correlation function. So here I'm showing a real space plot of this in the cylinder. The x and the y-axes are just the x and y-axis of the cylinder. And in 2 particular parts of the phase diagram. The bottom one is for a small value of j where we're in the superconductor. And you can see that the pair correlation function develops a stripe pattern. And indeed, basically the state there is essentially that the extra electrons in the problem are forming stripes, just like we're familiar with from small filling factors of a Landau level. On the other hand, if you go to larger j, you see that these variation in densities melt away, and you actually get an attractive hole at the origin, indicating that the electrons aren't repelling each other at short distances there. That's, of course, coming from the superconductivity. Okay, so that's the evidence for there being a superconductor separated by a phase transition from a charge density wave in this model. Why is that simple model a superconductor? It's a tiny twist on the models we're used to. All we did was we flipped the sign of the magnetic field in one of our quantum Hall bilayers. And the argument is that the Landau level topology causes electrons in this system to enter in the form of spin skirmions, like we're used to from quantum Hall ferromagnetism. And as I'll argue, when the skirmions become large, it allows them to efficiently avoid Coulomb repulsion because their charges spread out. And then the anti-ferromagnetism is going to cause them to bind into charge 2e pairs. So let's unpack this mechanism. First, just a brief review of skirmions and the quantum Hall effect. I think this is one of the most beautiful parts of the quantum Hall story, actually, in addition to the fractions, which is that if you're at odd integer filling, the existence of quantum Hall states there is also a strongly interacting phenomena. That's because the Zeeman splitting, of course, between up and down in gallium arsenide is actually quite small. But nevertheless, you see integer quantum Hall states at temperatures well below the Zeeman splitting, and that's coming from the interaction-driven quantum Hall ferromagnetism in the system, which causes the electrons to spin polarize even if the Zeeman field was absent. Okay, so if you're at filling nu equals 1, there's a finite spin density in the system. And if the Zeeman field is weak, naturally the direction of it is not very strongly pinned. So you could consider what happens if you put textures in the ferromagnetic order parameter. And then there's this beautiful series of work from the 90s showing that, in fact, if you put a skirmion texture into the spin density, that object carries charge directly and proportional to the Chern number of the Landau level, which is thus 1 or -1, depending on the sign of the magnetic field. Okay, to be a bit more quantitative, we know that skirmions actually come in 2 flavors according to the handedness of the way the field winds. That defines a topological charge for skirmions. And then the physical electron is proportional to the topological charge of the skyrmion with a prefactor, which is exactly the Chern number. And this has been seen in experiments from the large G factor, the odd integer quantum Hall states in NMR, for instance. Very beautiful physics. Okay, so how did these skyrmions show up in this problem and lead to superconductivity? Well, as I said, the superconductivity arises when you start at filling 2 and then add a small amount of density on top of that. So we should first understand what happens at just integer filling of 2 of the 4 Landau levels. Okay, so just like in quantum Hall ferromagnetism, it becomes favorable to, in the 4-component space to just pick 2 directions and then fill them completely uniformly in space in order to benefit from Coulomb exchange. But as usual, we have a degeneracy in how we want to fill 2 of the 4 Landau levels. This is where that anti-ferromagnetic coupling comes into play. As I said, it wants to anti-align the spins in the 2 layers. So here's how it would prefer to fill 2 of 4. It puts nu equals 1 of the filling in the bottom layer, nu equals 1 of the filling in the top layer, and then it does so in a way to anti-align their 2 spins. And because generally we're going to work with a small amount of easy plane anisotropy, the spin ordering is going to be in the XY plane. But J is small, so it's kind of floppy, so it doesn't matter. It doesn't mind too much actually canting into the Z plane when Z is weak. Okay, so in contrast to the usual quantum Hall effect where you have a single magnetic field, here you have opposite magnetic field in the 2 layers. So the Hall conductivities of the bottom, the filling in the bottom and the top layer cancel. So overall, there's no net Hall response here, even though the physics is still very simple, similar just to integer quantum Hall ferromagnetism. So we can indeed see that this is the preferred ground state when you don't dope the system. You can measure it by just looking at an order parameter for the XY anti-ferromagnetism, which is nothing other than the spin imbalance between the 2 layers. And again, because you have a continuous symmetry here, it doesn't directly order, but you see algebraic algebraic correlations at large distance. And we can also measure the gap to add an electron into this problem, and you see that it is indeed a very strong insulator with a gap of about twice the Coulomb scale. Okay, so where do the skyrmions come from? So what I'm going to imagine is I'm going to, if I plot the symmetry breaking in this problem, it's like I have 2 order parameters, the spin in the top layer, the spin in the bottom layer. And generally they prefer to be anti-aligned because of J. Okay, so the natural excitation you might first think to make is, as we're familiar with, we can make a skyrmion in, say, the spin configuration of just the top layer. That will carry charge E. However, there's a cost to this. Because there's anti-ferromagnetism between the 2 layers, the bottom layer effectively acts like a Zeeman layer for the top one. And because skyrmions require anti-aligning the spins in the region of the core, that's going to end up costing an energy in proportion to J. This will force the skyrmion to be small for the same reason that Shivaji first identified. And so their energetics are actually not very good. So single skyrmion is not really favored in this problem. However, suppose I instead make a skyrmion in the top layer, an anti-skyrmion, which is related by just taking the spin texture and just flipping it. I'm going to make an anti-skyrmion in the bottom layer. So let's suppose that the fields are just locked equal and opposite in the 2 layers. Okay, so now what happens is the anti-ferromagnetism is, of course, perfectly happy everywhere because it wants, N in the top layer to be opposite to the bottom layer. So J is now happy. Now you might think that this means that the net object has 0 charge because this is a skyrmion and an anti-skyrmion. Here's where the flip in the magnetic field was crucial. Because the charge is the Chern number times the charge of the skyrmion, on the top layer I have positive Chern number and positive topological charge, so that's Chern 1. The bottom layer, I have negative Chern number and negative topological charge, so the bottom layer also carries charge 1. So if you make these two skirmions on top of each other, it's actually a charge 2 boson rather than a neutral object. Okay. And the argument is the reason this becomes favorable is, of course, Coulomb repulsion, 1 over r, does not want them to be on top of each other. But because they're skirmions, it can spread out the charge to be very large, as I'll get into in just a second.
About 5 minutes left.
5 minutes? Okay, thanks. Yeah. Okay, so what's the numerical evidence that in the model, the charges actually enter in the form of skirmions? Because there's really, once you get into the energetics, there's competition here. Coulomb does not want them to bind into charge 2e, while the ferromagnetism sort of prefers this. So quantitatively, the thing we want to measure is you start from the insulator at nu equals 2, and then you measure the energy to add a pair of well-separated electrons versus the energy to add 2 electrons where they're allowed to be close to each other. And if you find a difference between these two, that exactly gives the binding energy for electrons to form pairs, which is going to tell us whether these charge 2 skirmions are favorable. And so we compute this in 2 ways. One, Shubayu did a very beautiful job analyzing the semi-classical nonlinear sigma model for the problem. And then we also can just directly compute excited state energies in DMRG. So before I go into it, let me give a little bit of the intuition for where the energetics come from, according to this nonlinear sigma model. The nonlinear sigma model description for usual quantum Hall ferromagnetism, you just have an order parameter n, a unit vector in each layer. There's a spin stiffness term, which wants it to be aligned in space. There's the usual Coulomb repulsion coming from the fact that wherever you make a topological texture, that carries charge, and those need to repel each other. And then all we do for our problem is we take 2 copies of it, one for the 2 layers, and then we antiferromagnetically couple them, but there's still Coulomb repulsion between them. So the basic competition that shows up is that if you make a skirmion of radius r, it's able to spread out its charge over a larger radius with no cost in the elastic energy g, at least if it's not easy plane. I won't really get into the easy plane part, but okay, so they're allowed to get big. So this causes Coulomb repulsion between the 2 skirmions to go down as 1 over r according to their size. But the attraction between the skirmions mediated by the antiferromagnetism is going as their area. So what this means is they can, if they grow large enough, the attraction will always win out over the repulsion, even if J is infinitesimally small. So this is what leads to binding at small j. So we can check this from the nonlinear sigma model by just solving for the classical ground state of the nonlinear sigma model. And what you find is as a function of J in the anisotropy, pair binding is preferred in this red region here. So as advertised, when there's no anisotropy, when lambda is 0, you find positive pair binding energy all the way down to infinitesimal J. When you put on finite lambda, this causes skirmions to deform into merons, and that increases their energy a bit. And eventually that causes the pairs to actually break. Okay, and then we can just compute the quantum energies in DMRG. That's the right curve here, and we find similar conclusions. We measure a finite pair binding energy once we extrapolate to the thermodynamic limit, actually for any j when lambda is equal to 0. And you can see maybe they're not quantitatively exactly the same, but the scales are quite similar, and Shubayu is actually able to understand the differences in the energetics by adding 0-point fluctuations on top of the nonlinear sigma model. Okay, final thing I want to mention is, we've shown that the skirmions want to bind into 2e, but that alone is not sufficient to show superconductivity. We also need phase stiffness or coherence to develop, and that comes from the fact that your bosons need to have a kinetic energy or a finite mass. So where does this come from? The mechanism is actually very similar to, for instance, physics that Kuhn-Yang has discussed for exciton condensates, or many others here for the energetics of the dispersion relation of composite fermions. And it comes from the interplay of the Lorentz force in the magnetic field and the antiferromagnetic mediation of an attractive force between them. So if you take this skirmion pair and boost it, because they see opposite magnetic fields in the 2 layers, This causes a Lorentz force between the two skyrmions, which actually separates them in space. So it pulls them apart, just like a dipole would form when you boost a particle-hole pair in the usual quantum Hall effect. But because there's a binding energy between these two electrons mediated by the interactions due to the antiferromagnetism, it costs energy to pull these electrons apart. So if you just work to lowest order in the separation between them, we then predict that the energy is a function of momentum, gives a quadratic dispersion relation with a mass whose scale is set by the interaction scale J. And eventually, if they get boosted too much, they get pulled apart and you expect the pair to break. We can't really get a dispersion relation super well in DMRG just because we have a small system size. So our momenta is very roughly quantized. But across different circumferences, we actually get a decent agreement with the mass predicted from that simple picture based on the actual excitation energies. So indeed, they do disperse. And you can actually see the pulling apart of the skyrmions when you look at the charge density wave in these bottom figures here. I plot what is the density of the charge to excitation along the cylinder as a function of the momentum. It starts out as one charge 2e blob, and then as you boost the pair, you see the blob split into two 1e's. That's exactly it getting torn apart by the Lorentz force. Okay, so I'll probably end up just stopping here, but that's then the explanation for why we see superconductivity in this model. We've shown that there's pairing due to the Skyrmion mechanism, and there's finite dispersion. So we expect a BEC condensate to form, and that's what leads to the superconductivity. Okay, and how much time do I have, Barry?
0.
Okay, yeah. The only thing I'd say is there's a nice way to understand this in terms of exciton condensates by applying a particle hole on one layer. Okay, and I'll skip the application to magic angle graphene.
Okay,
thanks,
great. Yeah, thank you, Mike, for that nice talk. So now we'll move into the question and answer